Hello, this is part 2 of the video for section 6.2. We're going to be looking at a few more examples. Here we have a system of two equations that involve x squared and y squared. So this is not a linear system. It doesn't really belong in this section, but I put it here because we actually can solve this system by the elimination method. We can add these two equations together, and the y squared and the negative y squared are going to cancel each other out. By the way, the graph looks like this. The first equation, x squared plus y squared equals 25, is the blue circle. The second equation, x squared minus y squared equals 7, is the red graph consisting of these two branches, and this is an example of a hyperbola. And maybe you can see from the graph that there are 4 different points where the two graphs of the two equations intersect. So like I said, we're going to add the two equations together, which results in 2x squared plus 0 equals 32. From here, I can divide both sides by 2 and get x squared equals 16. Which means x would equal the positive or negative square root of 16, plus or minus 4. Now, if we go ahead and stick positive or negative 4 back in for x, or just 16 for x squared in the top equation, it says 16 plus y squared equals 25. Then we can subtract 16 on both sides, and we get y squared equals 9. So y would equal the positive or negative square root of 9, plus or minus 3. So really, there are 4 different possibilities. X could be positive or negative 4, and either one of those could go with y being positive or negative 3. So we have the point 4, 3, the point 4, negative 3, the point negative 4, 3, and the point negative 4, negative 3. Next example, x minus y equals 1, 2x plus 4y equals 5. So we are back to a linear system. We know that this is only going to have one solution unless it doesn't have any at all, or unless it is a dependent system with infinitely many solutions. And we can use either one of the methods we talked about, the substitution method or the elimination method. Whichever one. They're about equally easy on this one. So if I wanted the substitution method, I could take the top equation, add y to both sides, get x equals 1 plus y, substitute it into the other equation. But instead, I think I'm going to use the elimination method, and there's more than one way I could do that. If I want to eliminate the x's, I could multiply the top equation by negative 2. Or if I want to eliminate the y's, I could multiply the top equation by positive 4. And I think that's what I'm going to do. I'm going to multiply everything on both sides of the top equation by just 4. And that will turn it into 4x minus 4y equals 4. The top equation, I'm just going to leave the way it is. I'm going to slide it over. And now the y's are all set up to kill each other off. So when I add the two equations together, I get 4x plus 2x is 6x. The minus 4y and the plus 4y just add up to 0. And on the other side of the equal sign, the 4 and the 5 add up to 9. So 6x equals 9. Divide both sides by 6, you get x equals 9 over 6, which is 3/2 in lowest terms. If you like decimals better, you could write it as 1.5. So we got a fraction, but that's okay, unless x stood for something that had to be a whole number. But yeah, you can have fractional solutions. And then if we go back and plug that in for x in, well, we could use either one, but I'll use the top equation because it looks a little simpler. 3/2 minus y equals 1. Subtract 3/2 on both sides, you get negative y equals negative 1/2. Divide both sides by negative 1, you get y equals 1/2. So we have our solution. X is, oops, that's backwards. Let me fix that. That's better. When we write our solutions as ordered pairs, we always want to put x first. So x is 3/2 and y is 1/2. 3/2 minus 1/2 does equal 2/2 or 1. And 2 times 3 over 2 would be 3. 4 times 1 over 2 would be 2, and the 3 plus the 2 do add up to 5. How about another example? 2x minus 3y equals 6, and y equals 2/3 x minus 2. Now, these two equations are not lined up the same way. So if I did want to solve this system by the elimination method, I would have to do some rearranging. I'd want to get an x term and a y term both on the same side in the bottom equation, like I have on the top equation. But since this bottom equation is already solved for y, seems like the most convenient thing to do would be to use the substitution method. I will substitute in 2/3 x minus 2 in place of the y in the top equation. So 2x minus 3 times 2/3 x minus 2 equals 6. Notice we have an equation here with only one variable left. It's all about x. So let's continue solving this. Remove the parentheses by distributing, multiplying out. We get 2x minus, and then 3 times 2 over 3 would just be 2x. Minus 3 times minus 2 would be plus 6. 2x minus 2x plus 6 equals 6. The 2x minus 2x kind of cancels out, leaves us with just plain 6 equals 6. So is that something that is just plain true, an identity? Or is it something that is just plain false, a contradiction? Well, this time we got the same number on both sides. That's an identity. And what does that tell me about my system? It tells me it's a dependent system. It's the kind where we have infinitely many solutions to the system, because anytime one equation is true, the other one automatically is as well. Every point on the line y equals 2/3 x minus 2, well, it obviously works in that equation, but it also works in the other one as well. So it would be a solution to the system. Okay, I'm going to end up with a couple of word problems. You have a box full of ants and spiders. There are 40 heads and 262 legs. How many of each, that is, how many ants and how many spiders, do you have in the box? So whenever faced with a word problem in math, I like to start by thinking, okay, what is it that they are asking us for? What are we trying to find? What will we have when we are all done and we say, okay, this is the answer to the question? Well, in this case, the question is, how many of each do you have in the box? So when we have our answer to that, that answer will consist of a number of ants and a number of spiders. So that's what we're trying to find. How many ants and how many spiders? Two unknowns that we're trying to find. Now we have to know, to solve the problem, that each ant and each spider just have one head each, but an ant, being an insect, has 6 legs, and then each spider has 8 legs. So that gives us our two equations. One where we count up the heads, 1 for each ant plus 1 for each spider equals 40 heads, and then another equation when we count up the legs. 6 for each ant plus 8 for each spider equals 262 legs. So there's our system. We could solve it either by the substitution method or by the elimination method. And just for the heck of it, I decided to use the substitution method. So I took the top equation, left the a where it was, but subtracted s on both sides so that it was solved for a. A equals 40 minus s. So, okay, 40 minus s, you go in for a in this second equation, which turns it into 60 times, there's where we made our substitution, 40 minus s plus 8s equals 262. From there, multiply this out to get rid of the parentheses, and we get 240 minus 6s plus 8s equals 262. Combine like terms. 240 plus 2s equals 262. Subtract 240 on both sides. 2s equals 22. Divide both sides by 2. S equals 11. And then A was 40 minus S. So now we know that's 40 minus 11, which is 29. And since A stood for how many ants and S stood for how many spiders, we have our answer, 29 ants and 11 spiders. And last example. On Monday, Archie paid $3.40 for 3 donuts and 2 coffees. On Tuesday, he paid $3.60 for 2 donuts and 3 coffees. On Wednesday, he was tired of paying the tab and went out for coffee by himself. What was the bill for 1 donut and 1 coffee? And I stole this out of an algebra book and don't remember whose book it was, but it's not something I made up. So I like to give credit where credit is due. And also, this is out of a book from several years ago, so the prices may not be current for donut and coffee prices. But what we're trying to find here, we really have 2 unknowns. Our final answer is just going to be the cost of 1 donut and 1 coffee. But we need to know what each of those 2 things is to be able to answer that question. So our 2 unknowns would be the price of a donut and the price of a coffee. And our 2 equations come from, well, the first equation comes from what happened on Monday. Archie bought 3 donuts that cost D dollars each, plus he bought 2 coffees that cost C dollars each, and that added up to a total of $3.40, 3.40. Then can you see what the equation for Tuesday would be? 2 donuts plus 3 coffees equals $3.60. 2D plus 3C equals 360. So there's our system. And I have chosen to solve this system by the elimination method. I wanted to eliminate the D's, although it would also work to eliminate the C's, but I decided to multiply the top equation by 2 to get a 6D here, and the bottom equation by -3 to get a -6D here. So after multiplying the top equation by 2, remember everything on both sides has to get multiplied by the same number. We get 6D plus 4C equals 680. Multiplying the bottom equation by -3, we get -6D minus 9C equals -1080. And when we add those equations together, we get -5C equals -4, $4. Divide both sides by -5, we get C equals 0.8. The calculator will show it as 0.8, but since it's money, I put an extra 0 and said it's 0.80, like 80 cents. And then stick that into either one of the equations. I use the top one, 3D plus 2 times 80 cents equals 340. 3D plus 160 equals 340. 3D equals 180. Divide both sides by 3, D equals 60. And we have our answer. Coffees cost 80 cents each. Donuts cost 60 cents each. So 1 donut and 1 coffee would cost a total of $1.40.